Good evening, everybody. Just getting back into the basics here with lecture 4 on humidity. So definitely before we get into the lecture, just want to thank you guys for the views and subscribers, as well as the likes. But definitely everything helps. If you can donate, please head on over to the PayPal link in the description. Anything helps, even $1. If you can't donate, no worries. You can always just like, subscribe, and share our videos. That definitely helps us. But alright guys, so this lecture will be on humidity. So this will be right along the lines back into the atmosphere. The last one was on dark matter, which is definitely an interesting lecture. Definitely check that out. I'll put the video link of that as well in the description. Alright guys, let's take a look at the humidity. So let's start out by talking about precipitation. So precipitation is a vital component of how water propagates through Earth's water cycle, connecting the ocean, land, and atmosphere. So definitely an interesting rainy day. It has been a rainy day sort of here in the Pittsburgh area, so definitely if you're venturing out over the next 4 days, definitely take your umbrella with you as well, because we do have some showers and thunderstorms in the forecast for the next 4 days. We'll definitely do a video on that later. But so let's continue this on humidity. So knowing where it rains, how much it rains, and the characteristic of falling rain or snow and hail allows scientists to better understand precipitation's impact on streams, rivers, surface runoff, and groundwater. Frequent and detailed measurements help scientists generate models of and determine changes in Earth's water cycle. So depicted on the screen here is the average rainfall per year in each area. So the Pittsburgh area, we're about 38.5. Well, I'd say maybe 28.6 to 38.49 inches of rain. So it's definitely interesting. And you can see some areas, especially down here in South America. Let me get the pointer going here. So areas down here in South America, you guys are getting above 196 inches. So it's definitely pretty intense precipitation. But moving on to the water cycle. So the water cycle describes how water evaporates from the surface of the earth. So take a look at evaporation. It rises into the atmosphere, cools, and condenses into rain. or snow in clouds and falls again to the surface as precipitation. Water falling on land collects in rivers, lakes, soil, and porous layers of rock. Much of it flows back into the oceans, where it will once again evaporate, thus starting the cycle all over again. The cycling of water in and out of the atmosphere is a sufficient aspect of the weather patterns on Earth. It's definitely pretty interesting. Let's go back to that image and we better describe this. So, water evaporates from oceans, lakes, and streams, and condensation occurs, forming clouds. Transpiration from plants and trees evaporates up in the atmosphere. Then you have precipitation forming over mountainous regions, flows down the mountains as surface runoff goes into the groundwater, and then it all starts over again. So it's definitely pretty interesting. So within the atmosphere, water is unique in that it can exist in all three phases. So we have solid, liquid, as well as gas in the atmosphere. And then we also have topics known as latent heat versus sensible heat. Let's start out with latent heat here at the bottom. Latent heat results in a phase change of water. So we have 212-degree water sitting here. Latent heat transforms that into a gas at 212 degrees. And then sensible heat here results in a change in temperature of the water. So we have 60-degree water here. Sensible heat occurs. And then we just have a temperature change. So it's still liquid water, 212 degrees. There's no gaseous form of water as it is with latent heat. So it's definitely an interesting aspect in the atmosphere. We'll get into more of that as well as we continue. So the water cycle is in balance, so that evaporation and transpiration equals the rate of precipitation in the atmosphere. Little interesting fact on the side here, a water molecule has an atmospheric lifetime of about 10 days. So each molecule of water in the atmosphere can survive up to about 10 days. So it's definitely pretty interesting to take a look at that. But let's take a look at the type of phase changes of water. First, we're going to look at evaporation. So evaporation, liquid to vapor, absorbs heat. So there are several factors that determine the evaporation rate of liquid water. This is important to meteorology since the amount of moisture that evaporates into the air leads to changes in the weather. So let's go into some explanations of this. Temperature of water. The water molecules move faster as water warms. The faster the molecules move, the more easily they can escape the surface. So a warm lake or ocean will evaporate a large amount of moisture. This moisture can be used to generate precipitation. And then temperature of the air. As the air above the water warms, it has the capacity to have a greater amount of moisture evaporated into the air. If the air is cold, it is difficult to evaporate a large amount of moisture into the air even when the water is warm. A combination of warm water and warm air will evaporate the most water. And then wind speed. So a higher wind or higher wind speed helps remove moisture that has been evaporated from the water. This helps the relative humidity stay unsaturated near the water surface. When the air is saturated, the amount of moisture that evaporates into the air is minimized. Higher winds will continue to supply drier air from aloft to the water surface, and this allows for a greater amount of evaporation. A higher wind also churns the water, waves, and splashing, and this helps lead to a greater surface area in which evaporation can occur from the water surface. And then dry air. Dry air will help generate more evaporation, especially if the air is warm and dry. There is a higher capacity to evaporate moisture into the air as the air dries. Once the air is saturated, then the evaporation rate is minimized. Air with a low relative humidity is optimum for moisture to evaporate into it. And then sunlight. So sunlight, or direct sunlight, will lead to more evaporation. The direct photons of light increase the motion of the water molecules it strikes, giving them a better chance to evaporate, escaping the water surface. All right, let's take a look at condensation. So this is vapor to liquid. It releases heat, a process by which water vapor changes from a gaseous state to a liquid state. If air is cold below its dew point, some part of water vapor changes to liquid. Condensation in the air does not take place automatically as it happens in the sealed water container. Let's take a look. Let's take a look at the effects here. So in a sealed container, after saturation is reached, water vapor begins condensing back into the water. But in the atmosphere, condensation is not a simple process. There is a prerequisite condition for the condensation of water vapor, that there must be some surface on which water vapor can condense at the dew point. The surface for condensation of water vapor is provided by the condensation nuclei, which are present in large numbers in the atmosphere. Hence, the condensation of water vapor in the atmosphere takes place only if sufficient numbers of condensation nuclei are present. So the prerequisite conditions for condensation: sufficient amount of water vapor should be available in the air. Saturation of air is achieved by decreasing the temperature or by adding water vapor into it. And a sufficient number of condensation nuclei should be available. In the absence of condensation nuclei, condensation may not start even if relative humidity exceeds 100%. But there is always a large number of dust particles in the air. Under such conditions, relative humidity rarely exceeds 101%. On the other hand, hygroscopic nuclei have a great affinity for water vapor. Therefore, condensation can start even if relative humidity is far less than 100%. Later on, when the relative humidity reaches close to 100%, the water droplets grow in size. Such types of conditions are essential for the formation of clouds. The only way by which large amounts of water vapor in the atmosphere can be converted into liquid is condensation, and to solid is sublimation, which leads to the reduction in the temperature of the air close to or below the dew point. The invisible moisture of the atmosphere is changed into a variety of forms. If the atmosphere is cold, its capacity for holding water is reduced, and if it is sufficiently lowered, then condensation takes place. The form of which water vapors condense is determined by the conditions under which the cooling takes place. So we have a few processes here of condensation. We have loss of heat by radiation, contact with cold surfaces such as a cool ground, leaves of plants, layers of snow, and icebergs. We also have mixing with cold air, and then we have no actual addition or withdrawal of heat. This type of temperature changes results from internal processes in adiabatic change. So adiabatic cooling by expansion and rising air currents. Let's take a look at adiabatic processes. So adiabatic process is defined as the process in which no heat is added or subtracted from the air mass. A process of adiabatic or expansion cooling depends in the first instance on the parcel of air mass rising through the atmosphere to higher elevations. The temperature changes involving no subtraction or addition of heat are called adiabatic temperature changes. Air is a poor conductor of heat. Therefore, vertically moving air mass retained its heat energy, keeping its thermal identity different from the surrounding air. When air mass rises, it expands due to decrease in pressure at higher elevations. As a result, the volume of this rising air mass increases due to expansion. So during expansion, the air mass has to do work against the surrounding air during this process. Internal heat energy of the air mass is consumed due to expansion, reducing thermal energy per unit volume, resulting in a decrease in temperature. The rate of decrease of temperature of the moving air mass with height is called the adiabatic lapse rate. If the air mass remains dry, the rate of decrease of temperature is called the dry adiabatic lapse rate. The value of the dry adiabatic lapse rate is about 10 degrees Celsius per kilometer. It is different from the normal lapse rate. It is also called the environmental lapse rate, which is recorded by the thermometer, carried through the atmosphere by a rising weather balloon. The temperature of the rising air mass continues to decrease until it becomes saturated. Further cooling of the air mass results in condensation. During condensation, water vapor is converted into liquid, releasing latent heat of condensation. The latent heat of condensation mixes with the moving air mass. As a result, the parcel of air mass cools more slowly than the dry adiabatic lapse rate. The lower cooling rate is called the saturated adiabatic lapse rate. Generally, its value remains around 5 degrees C per kilometer. However, its value varies from about 4 degrees C per kilometer for very humid air in the equatorial regions to about 9 degrees C per kilometer for cold air in the polar regions. Condensation, therefore, depends upon two variables, which is the amount of cooling and relative humidity in the air. So there are various types of condensation. We'll take a look at those. So we have dew. Dew forms directly by condensation near the ground. When the surface has been cooled by outgoing radiation, dew formation mainly occurs when the nights are clear and the wind is calm. Generally, dew forms on the grass, on the leaves of plants, and many other solid objects near the ground surface. Conditions favorable for dew include radiational cooling during the night, calm conditions and light winds, clear sky, cool and long nights, sufficient availability of water vapor, anticyclonic wind, and cold air advection. So conditions that are not favorable for dew include cloudy skies, strong surface winds, the presence of a cyclonic circulation, or warm air advection. And we'll take a look at the next process of fog. It's definitely another interesting process. So fog results from the condensation of atmospheric water vapor into water droplets that remain suspended in the air in sufficient concentrations to reduce the surface visibility. Fog is simply a cloud layer very close to the surface. It is a major hazard in the industrial area. It is very common during the winter. It is also very common near coastal areas as well. Conditions favorable for fog include excessive moisture, relative humidity should be greater than 75%, calm light winds, and anticyclonic winds. We do have various types of fogs, so let's take a look at the first one. The first type of fog is called frontal fog. When warm rains fall through cold air, fog or stratus clouds form at the frontal surface due to supersaturation caused by evaporation from warm rain into the cold air. So the next type of fog is called steam fog. It is an unstable type of fog produced by intense evaporation from the water surface into relatively cold air. Steam fog is found in the mid-latitudes in the vicinity of lakes and rivers in the autumn when water surfaces are still warm and the air is beginning to cool. And we also have a phenomenon known as advection fog. Advection fog is produced by the transport of warm, moist air over a colder surface, resulting in the cooling of the surface layers below their dew points, with the condensation taking place in the form of fog. It can also be produced if the cold air mass moves across the warm water surface. We also have a phenomenon called radiation fog. Radiation fog, or ground fog, is produced when stagnant, moist air is in contact with the ground that has become progressively cooler during the night because of excessive outgoing radiation. Another type is called inversion fog. So it is the name given to any type of fog or stratus cloud that initially develops at the top of a moist layer, accompanied by subsidence above the inversion. It intensifies the latter and produces the stratus cloud that may build down to the ground as fog. It's definitely an interesting one there. I see that multiple times in our area. And then we'll talk about upslope fog. Upslope fog is a stable type of fog resulting from the gradual orographic uplifting of convectively stable air. The air cools adiabatically, and the fog begins to form when it reaches an elevation where the air has cooled to saturation. So while we're looking at fog, we should definitely take a look at the topic of frost. So frost, it is not the frozen dew. Frost occurs when the dew points of the air falls below the freezing point, or 0 degrees Celsius. When condensation starts with a temperature below 0 degrees Celsius, the water vapor in the air passes directly from the gaseous to solid state, which is known as sublimation. Frost may be light or heavy. When the frost is heavy, crops are damaged. It is also called killing frost. Frosty nights are more common during the winter season in northwest India. The crops, which are sensitive to low temperature injury, suffer great damage. So we have different types of frost. So let's take a look at radiation frost. The radiation frost occurs on calm, clear nights when terrestrial radiation is lost to space. The absence of clouds and heavy concentration of water vapor leads to the formation of radiation frost. We have another type of frost called advection frost. So advection frost occurs in those areas where cold air is advected from the colder areas by stronger winds. Advective frost or wind frost can occur on any time of the day or night, irrespective of the sky conditions. In some cases, the advective frost may be intensified by radiation frost. We also have a frost known as white frost. White frost is caused by the sublimation of ice crystals on objects such as tree branches, wires, etc. These objects must be at a temperature below freezing, as air with a dew point below freezing is brought to saturation by cooling. And the last frost we have is known as black frost. Black frost occurs when vegetation is frozen because of a reduction in the temperature of air that does not contain sufficient moisture. So that's definitely an interesting thing there. Sometimes see that in West Virginia there. So while we're talking about frost, dew, things like that, let's take a look at smog. So smog is the combination of fog and smoke, which is found over big industrial cities in the middle or high latitudes. Since it persists for days together and causes so many diseases and death, therefore it is also known as a killer fog. Now let's take a look at condensation just above the ground. So during the summer season, the air mass at the ground surface is heated due to intense heat energy. This air mass becomes warmer as compared to the surrounding environment. Strong vertical currents are generated, which uplifts the warm and light air mass. The rising air mass gets saturated due to cooling. Further cooling of the saturated air mass leads to condensation. The uplift of the air mass continues even though the original cause of the uplift has ceased to be effective. Later on, upward movement of the air is caused by the buoyancy force. Often the air mass sinks back to the former level that it once was, and the upward and downward movement of the air mass depends upon the stability and instability of the atmosphere. So let's take a look at phase changes. So we have melting. So we have melting here, so it goes from solid to a liquid, and that absorbs heat. And then we have freezing, that goes from a liquid to a solid, that releases heat. And then we have sublimation, that goes from solid to vapor, or gas, you could say, that absorbs heat. And then we have deposition, that goes from a vapor or gas to a solid, and that releases heat. All right, so let's take a look at, start with vapor pressure here, guys. Definitely another interesting topic in meteorology. This actually got me pretty good in college, actually. It was kind of hard to grasp this topic, but I hope I can get you guys on the same page here. So vapor pressure is the total part of total atmospheric pressure attributable to water vapor. If there are too many water molecules in a given volume, they may begin to stick together to form liquid droplets. This is called the saturation point. And the vapor pressure at this point is called the saturation vapor pressure. Any addition of water molecules after saturation will result in the formation of more liquid droplets. A commonly made statement is that air can only hold so much water vapor, and that when this amount is reached, the air is saturated. Though it may be helpful to think of it in these terms, this is technically not correct, since saturation would be reached whether or not there was air present in the volume. And let's take a look at the saturation vapor pressure. So saturation vapor pressure increases with increasing temperature. A warm volume of gas would have a higher saturation vapor pressure than a cold volume of gas. So it's definitely pretty interesting there. So the process of evaporation in a closed container will proceed until there are as many molecules returning to the liquid as there are escaping. At this point, the vapor is said to be saturated, and the pressure of that vapor, usually expressed in millimeters of mercury, is called saturated vapor pressure. Since the molecular kinetic energy is greater at higher temperature, more molecules can escape the surface, and the saturation vapor pressure is correspondingly higher. If the liquid is open to the air, then the vapor pressure is seen as a partial pressure along with the other constituents of air. The temperature at which the vapor pressure is equal to the atmospheric pressure is called the boiling point. So it's definitely pretty interesting there. So let's take a look at relative humidity, what this lecture is all about. So relative humidity is a ratio of vapor pressure to saturation water vapor pressure. For example, if the vapor pressure is 10 millibars and the saturation vapor pressure is at 14 millibars, then the relative humidity is 10 divided by 14 times 100%, which is equal to 71.4%. So two ways to change relative humidity are to change the water vapor content or change the temperature. So that's definitely pretty interesting there. So we can see 10% relative humidity in the beaker to the left, 90% relative humidity in the beaker to the right. You can see more water molecules are present within the right beaker here due to the increased relative humidity values. All right, let's take a look at the dew point. So the dew point is a temperature to which air must be cooled in order to reach saturation. Higher dew point indicates that air contains more moisture. If saturation occurs below 32 degrees Fahrenheit, then this is referred to as the frost point. Dew point is a measure of actual moisture content, not relative moisture content. An increase of 10 degrees C or 18 degrees Fahrenheit in dew point means a doubling of moisture. So dew points above 70%, dew points above 70 degrees mean very, very moist air. You can see here temperature at 55 degrees, relative humidity is 100%, dew point of 55 degrees. Temperature 95 degrees here in the right, relative humidity 50%, dew point is 74 degrees. You can see there is a lot more moisture. So we can actually measure this as well. So an instrument that measures humidity is called a hygrometer. We can take a look at the hair hygrometer. So a hair hygrometer uses the lengthening or shrinking of hair as a humidity determiner. So that's definitely an interesting topic. I think I've seen one of those at college before. They're kind of rare to see up in person, but they're pretty cool. And then we can take a look at a psychrometer. So this is a type of hygrometer, and it is one of the most accurate ways to determine the dew point and the relative humidity. A psychrometer uses a thermometer with a moistened bulb called the wet bulb thermometer to measure the wet bulb temperature. It compares this temperature with the dry bulb temperature, which is just the air temperature, and uses special tables to determine dew point and relative humidity. The larger the difference between the wet bulb and dry bulb temperatures, the drier the air is. Let's take a look at that. Wet bulb versus dry bulb. So the wet bulb temperature is the lowest temperature that can be reached under current ambient conditions by the evaporation of water only. And the dry bulb temperature is the temperature of air measured by a thermometer freely exposed to the air, but shielded from radiation and moisture. And then I have a few equations here I wanted to show you guys just to show. Let's see. So here is the wet bulb temperature calculation. So this is the partial pressure of water vapor. So this is equal to the saturation pressure of water vapor at wet bulb temperature. And this is subtracted by the total pressure or barometric pressure minus the saturation pressure of water vapor at the wet bulb. This is multiplied by the temperature of the dry bulb temperature and the wet bulb temperature, divided by 1555.56 minus 0.722 times the wet bulb temperature. So it's kind of a confusing formula, but it's actually pretty interesting. And then the next one we have This one is a little bit more tedious. So this is the humidity. So taking a look at this, we have 100 times the exponential of 1.8096 plus the quantity of 17.2694 times the temperature of the wet bulb divided by 237.3 plus the temperature of the wet bulb. And you subtract that by 7.866 times 10 to the minus fourth times the pressure, multiplied by the air temperature minus the wet bulb temperature, multiply that by 1 plus the wet bulb temperature divided by 610. And that entire expression there is divided by the exponential of 1.8096 plus this value here, except you change the wet bulb temperature to the actual air temperature. So it's definitely interesting. There's probably a little bit more that I could add into humidity, but for purposes of this lecture series, this is probably as far as I'm going to go with humidity. There are a couple more calculations I could add, but I don't want it to be too confusing. But it's definitely an interesting topic. Definitely humidity goes along with dew points, fog, frost, things like that. So it's definitely pretty good. Dew point is definitely oppressive today, or at least it was. The dew point was about 75 degrees earlier today, so it was almost, walking into a can of soup outside. It was insane. And that looks to be expected for the rest of the week here in the Pittsburgh area. So we're looking at dew points of 68 degrees all the way up to 74 degrees. So it's definitely going to be an interesting week. Definitely a wild week in weather. Definitely some derecho activity that happened earlier today. But yeah, we're definitely going to be taking a look at the tropics in the next couple days. It looks like there is a couple waves coming off of Africa, so we're definitely going to see what happens with those. Wind shear is pretty prominent right now, so we'll see if that those systems can transform into anything. But all right, guys, as I stated earlier, the music in the intro and the outro is provided by Guitars and Ghosts. Definitely check his YouTube channel out and subscribe and like his videos. Definitely a badass musician. But definitely, guys, and if you guys have the the means to donate, we definitely appreciate it. Anything helps, even $1. But that would be at paypal.me/World Weather Authority. We will put that link in the description as well. But definitely like this video, guys, if you enjoyed it. Definitely share it. Definitely consider subscribing to the YouTube channel, as well as following us on Facebook at facebook.com/World Weather Authority. That's where we have the live streaming of the drone. Right now, you have to have a whole bunch of, or a plethora of different values for YouTube to go live. You have to have 1,000 subscribers plus a certain number of views and things like that. But we're definitely going to get there. I have no doubt. All right, guys. Thank you for joining me. And hopefully I can get Justin in on some of these lectures, because I know he'll definitely be interested in some of the next upcoming ones. So the next lecture will actually be on atmospheric stability. So that'll definitely be a pretty interesting lecture. We do have one later on thunderstorms. We do have one on mesoscale convective systems, lightning, atmospheric phenomenon. So definitely stay tuned for those. Yeah, guys, we definitely appreciate it. Thank you. Never stop chasing.